Hi Chem 240, this is Dr. Ricardo. We are going to be doing the last video, which will be the fourth video in chapter 20, which is on electrochemistry. So we are going to pick up with the concept of electrical work. So electrical work is going to be equal to the amount of charge that moves between the cells multiplied by what the voltage is. So a nice analogy on the electrical work the maximum amount of electrical work that we can get out, we're going to call W max. Now this is going to relate back to chapter 19 when we talked about delta G, right? Delta G was the free energy in a chemical reaction. Well, guess what? The free energy is the maximum amount of useful work that you can get out of a process. So if your process is an electrochemical process, then W work, right, the maximum work, or W max, is going to be equal to delta G for that particular chemical reaction. Remember, the free energy is the amount of energy that can go towards doing something useful. And so electrical work that you could harness, the amount of work that a battery could do would be W max, and it would also be equal to delta G in that situation. Okay, so I want to show you that waterfall picture again, okay, because I think it does a great job of, it's a great analogy for what's happening with our electrical situation. If I think about water flowing over a waterfall, I have two things that I have to put into the equation to talk about how much work that waterfall could possibly do, how much mechanical work it could do. So the first thing is, what's the height of the waterfall? Well, the height of the waterfall is its potential energy, right? So that's the distance from the top of the waterfall to the bottom of the waterfall. The bigger the waterfall, the more potential it has to do energy, more potential it has to do work. Makes sense, right? Niagara Falls has a very large height, and that's part of the reason why you can harness a lot of Niagara Falls energy and use it to run it through a turbine in a hydroelectric plant to make electricity. So the potential is going to be really important. So what does that correspond to in our situation, an electrochemical situation? It's the potential between how negative the anode is and how positive the cathode is. So in our voltaic cell, it's this difference, and we think of the flow of electrons naturally going downhill from negative to positive. If I have something that was double the voltage, let's say this is a 9-volt battery and I made it an 18-volt battery, I could kind of consider that being twice as high. So it's got twice as much potential. Okay, so the voltage is related to the potential, the height difference in a physical situation. Okay, well, what's the other factor? The other factor that's important to determine how much energy something can deliver is how much water is flowing over it, right? If I have a very high waterfall, but it's only a teeny bit of water flowing over it, that's going to be a lot less than if this whole area up here has water flying across it like it might in the springtime. Maybe this is in the wintertime, right? So in the springtime when there's so much water, there'll be that much more water flowing over it. Well, what does that correspond to? Well, for us, that quantity corresponds to the total electric charge. So Q is the amount of electric charge transferred per mole of reaction, and what units it's going to be in? It's going to be in the metric system unit for electric charge, which is going to be coulombs, okay? So we're going to have coulombs here multiplied by volts, okay? And a volt is a joule per coulomb. So if you multiply joules per coulombs times coulombs, you're going to get joules, which makes sense because that's the unit for work, right? Or energy. Remember, work and energy have the same units. Okay, so we just figured out that the amount of energy or the amount of work was going to be Q times V, right? I'll write this a little bigger. So W was equal to Q times V. We take the voltage, multiplied it by the amount of electric charge, and we can get the work, the maximum amount of work that we can get out of the system. And we said that that's equal to delta G for that particular process, because it's only the free energy that can go towards doing work. Well, what happens if we want to measure the current, right? And so what's the current? The current is the amount of charge, right, that's being transferred per unit time. Well, current for us, the symbol is I, and I have I times V, and what that's going to give me is that's going to give me the power, or the maximum power that I can get out. Because what is power? Power is work per unit time. So if I take the current, the Q, and I divide it by T, I basically get the time in the denominator. And if I just sort of rearrange this, you get the way you usually see it. It's just P is equal to V times I. Okay? And so if you take a physics class, the power in an electric circuit is equal to the voltage going through it times the current going through it. Okay? So let me show you very quickly why this is true, that power is equal to work divided by time. So what I can do over here is leave my volts alone and put in what I is, right? So what did we say I is? The amount of current flowing is the electric charge divided by time. So the faster it flows, the more current you have, right? So go back to our waterfall, right? We've got the amount of water and we got how fast it's flowing. So even if you had a lot of water coming over the waterfall, but it was flowing slowly, that would be a lot of energy, but the power wouldn't be very high because it was going slowly. So the maximum situation to get the most electrical power is you want to have a high voltage, you want to have a lot of water, and you want the water to be flowing fast, which makes sense, right? So what do I have? This is the potential, right? Times the amount of water, right? That's the current, in our case, the amount of electrons, divided by how much time. So the shorter the amount of time, the higher the power. Okay, let's do one more thing to V, because I want to show you that I get this in a traditional sense of power of work divided by time. Okay, so what's V? Voltage, guys, is just charge per unit it's just work per unit charge. So if this is voltage and this is current, what happens is the Q's cancel out and I get power is equal to work over time, and that's what we always saw, right? This would be, if I was doing units, this would be in seconds, right? So joules per second is work per unit time. Okay, so this should make sense to you. If I want to measure the power in an electrochemical cell, I just need the voltage times the current. If I want to get the work, I need the charge times the voltage. Okay? All right, so that being said, let's take a look. Let's end of the physics lesson. Okay, let's get back to chemistry. So Q is the amount of electric charge transferred per mole of reaction. So Q is equal to N times F, where N is the number of electrons transferred for each mole of reaction. So if I had a particular electrochemical system and I put together the two half reactions and I saw that the top half reaction was a 6-electron oxidation and the bottom half reaction was a 6-electron reduction, remember those always have to cancel out, then my N would be 6. It's the number of electrons transferred per mole of reaction the way it's written. Okay, so that's pretty easy to figure out. And what's F? Well, F makes sense, right? If we're talking about moles of electrons that are transferred through the circuit, I just need to figure out what is the charge on 1 mole of electrons. So if I took a bag of electrons, okay, and I put them together, what would their total electric charge be? Well, remember, each electron has a tiny electric charge in coulombs. Each electron is 1 times 10 to the minus 19th coulombs. That's because they're so small. But in a mole of electrons, there's a lot of electrons. So the way I get this number, the number of coulombs per moles of electrons, is I multiply the charge on an individual electron, okay, which is 1.6 times 10 to the minus 19th times Avogadro's number, because that's how many electrons are in a mole. Put those very big number and a very small number together, and I get a medium-sized number. I get the Faraday constant, F. So that's 96,500 coulombs per moles of electrons. Okay, so go back up to here. This Q now, for us, is going to be minus N times F, okay? Why the minus sign? Because this is going to be, if the electrons are flowing naturally, the minus sign is in there because this is going to be an exothermic process. It's going to give off energy if the electrons are flowing naturally. So you need to take E for the cell, which is a positive number, right? That's spontaneous. You need to put this negative sign in here, so now it corresponds with G. Okay, so we take the number of electrons that are transferred in that particular reaction, multiply it by this constant, just grab the same number every single time, 96,500, times the voltage of the cell, right? The overall voltage of the cell, which is E ox plus E red. So that's it. That's W max. So let's quickly take a look at the units. We want work to come out in joules per mole of reaction, the way it's written. So we have, this is the number of moles of electrons transferred, right? That's the 6 per mole, moles of electrons per mole of reaction. Okay, this F is coulombs per mole of electrons, so moles of electrons cancel out. And what's joules? What is cell potential? It's volts, so that's joules per coulomb. So the coulombs cancel, the moles of electrons cancel, and I get joules per mole, which is what I should get. Okay, so let's equate our new formula, which is W max is equal to minus N times F times E for the cell. Okay, well, if we did this under standard conditions, you could put little zeros over here, right? But under any conditions, this is the way we have it currently written. Well, we know back from chapter 18 that delta G is equal to W max. That's the definition of the free energy. So we can substitute in delta G for W max here. And I get a very handy formula. If I want to know what delta G is under any circumstances, I just take minus the number of electrons transferred in the cell, right, per reaction, times the Faraday, times the voltage. So these two basically are constants, right? This depends on the particular reaction, and this is your voltage, your cell voltage. Okay. If I'm working at standard conditions, which we know what standard conditions are, right? Nothing to do with the temperature, but all concentrations have to be 1 molar, and all pressures, if there's any gases involved, the partial pressure of each gas has to be at 1 atmosphere. So delta G0 is equal to minus NF E0 for the cell. The E0s for the cell, guys, are in the cell potential. We can get those by the standard half reactions. And so basically, you can correlate these electrochemical tables here, right, with our, so here's the electrochemistry, standard electrode potentials. These are E0s for the cells written as reduction. So you put your reduction half reaction together with your oxidation half reaction. You turn one of them around because these are always written as reduction. You get the overall E for the cell. If you put it through our little new formula, this one right here, you should take that E0 from this page, right, that you calculate from the oxidation potential and the reduction potential from this page, multiply it by the Faraday constant and the number of electrons transferred, stick a negative sign on it, you should get the same exact number that you would have gotten if you did that chemical reaction by doing delta G of formation calculations. Let me just make this bigger. Right, so if I had my particular chemical reaction and I wrote it out, I can always calculate delta G for that reaction by taking the products minus the reactants, and the coefficients get multiplied by each of them. So it's products minus reactants where I include the coefficients. Okay, so be very careful to look up the right stuff. But this number here, delta G, that you get for putting together an electrochemical reaction should match up with this number that you get from here, right? If you just use our new formula. That's the relation between those two tables. Okay. Again, both of these tables are at 298, so this would also be at 298. Okay. So if we want to tabulate tabulating standard electrode potentials, E-red, they're only tabulated as reduction potentials. I already told you this. And all the solutions are 1 molar, and all partial pressures of gases are 1 atmosphere, and the temperature is specified to be 25 degrees. So we know under any conditions, E for the cell is equal to E ox for the cell plus E red for the cell. So you'd have to measure those if you were at different conditions, or put them through a formula that I'm going to show you now. But if you're under standard conditions, you just look them up in the back of the table. E for the cell is equal to E ox for the cell, so figure out what's being oxidized, look it up, right? Figure out what's being reduced, look it up. Remember, the one that's oxidized, you have to turn it around, so you're going to have to change the sign on it. If you look it up under reduction and it's 0.76 and you want it as oxidation, you have to slap a negative sign on it and make it negative 0.76. So the oxidation one has got to get turned around. The reduction, you leave it alone. And that's just because the way the table is written. They didn't want to make the table twice as long, so they didn't give you all the oxidations and then on a different page give you all the reductions, because they're the same thing. You just have to flip them around. So you can just change the sign, but one of them is always going to get switched. Okay, so what's the relationship in electrochemistry that's very similar to the delta G is equal to delta G0 plus RT ln of Q? Well, the relationship for electrochemistry is, if you want to know E for the cell under non-standard conditions, right, all you have to do is take E0 for the cell, which you look up in the back of the book by doing this, right? Get the reduction, get the oxidation, turn the oxidation around, add them up. Minus RT over NF ln of Q. So Q takes care of the fact that if anything is non-standard, those numbers won't be ones in there anymore. And then the log of 1 won't give you 0, right? Remember, if these things are all ones in here, right? 1 times 1 times 1. I don't care how many ones you have. Look, these are all ones under standard conditions. This whole term cancels out, right? The natural log of 1 is equal to 0. So E for the cell under standard conditions is equal to E for the cell. Well, if I put all ones in here, I have standard conditions. If I have other numbers, different concentrations, or different partial pressures, all I have to do is put it through this formula. Here's the LOG version of it, okay? So basically, what's nice about this is, since this is a constant, right? And if you're doing it at 298, and you can put all of these constants in here. You can put the 8.31, the 298. You can put the Faraday in. And those three constants together, right? RT over F comes out to 0.0592. So if you're doing this in volts at 25 degrees and you just want to see what's the difference by changing the concentrations or the partial pressures, you can get this version of it. So this is the general version at any temperatures, okay? And this is the version of it when you're at 25 degrees and just the concentrations and the partial pressures change. Remember, be careful. If you're going to use this one, here you use LOG, so that 2.3 factor between the natural log and the log base 10 is already in there. So this is RT over F with the 2.3 in, and that would give you that. Okay? So this is the way people usually work with it. Okay. Now the other cool thing is, if you wanted to do this for any half reaction, you could too. For instance, if you wanted to know E reduction under non-standard conditions, so just put a RED in there, you would just look up E0 reduction and then put it through this formula. Again, this is Q, is called the reaction quotient. It's the products, the concentration of the products divided by the concentration of the reactants, where you take care of the coefficients, right? The coefficients become the exponents here, right? When you're just doing the delta G's from the tables, the coefficients just get multiplied. Okay, so other thing that you can do then is really cool, like we did last time, is at the very bottom of page 21. From chapter 18, we learned that when you're at equilibrium, you're not just under any reaction conditions, you're at the very special place where you're at the equilibrium conditions. So Q, the reaction quotient is going to be equal to the equilibrium constant, right, when you're at equilibrium. The other thing that's going to occur if you're at equilibrium is defined as delta G equal to 0. So do what we did before. Let's take the one on the top. I got to put a Q in here, and I got to make this guy equal to 0, right? Because there will be no voltage if I'm at equilibrium, right? Every battery is out of equilibrium, right? It's ready to go spontaneous. So if the battery dies, that's when it's at equilibrium, when there's 0 volts. So you put a 0 here and you put a K here, and now what do? You just rearrange this, bring this over to the other side, and I get this nice little formula that at equilibrium, 0 is equal to E0 for the cell minus RT ln Kf, and then the last thing that you would do to that is just bring the bring this over to the other side, right? So that you get rid of the minus sign. This is page 22. So at equilibrium, E0 for the cell is equal to RT ln Kf. So if you have an electrochemical cell and you know its standard cell potential, you can calculate the equilibrium constant, okay? If this number is positive, then K is going to be positive. Look, there's no negative signs. If this number is negative, then K is going to be a fraction. It's going to be a tiny number, which makes sense, right? The equilibrium constant will be a very small number for something that's non-spontaneous. So for ours, if we have a spontaneous reaction and the overall cell voltage comes out to be 1.1, then basically I'm going to have 1.1 times NF divided by RT. That whole thing is still going to be a positive number. And I'm going to then raise E to that number. So K will definitely be positive. Okay? All right, again, if you don't want to work with all of those constants, you can factor out or basically plug in the R, the T, make it 298 over F, and change this to LOG. Okay? And you can do that as long as you're at 25 degrees, which is most of the time where we're going to be working. And you can get that E0 for the cell is going to be equal to this combination of constants divided by N, right? Where N is the number of electrons transferred times the log of the equilibrium constant. So what are you doing? Relating equilibrium constant to the voltage of the cell under standard conditions. Okay. So the last thing that we're going to talk about are electrochemical cells. So electrochemical cells are the types of cells that don't occur naturally, right? You have to force them to occur. So by definition, they're non-spontaneous, okay? Now the cool thing about them is you don't have to take such care to separate the reactants before they react, right? You can have them in the same vessel. And the reason is they don't react spontaneously. So you can stick both electrodes sometimes right into the same solution. And that's one of the examples that we're going to do right now. And you can cause a chemical reaction to occur at the electrode tips that wouldn't otherwise occur in the solution. And the reason is you're providing the energy electrically. You're providing that difference. You're forcing the electrons in. Okay? So we know it's non-spontaneous. So therefore, from chapter 18, delta G for the reaction is going to be positive. And we learned the relationship just now that between delta G and E is they always have the opposite sign. So what's E for the cell? E for the cell is how many volts it gives off. Okay, so if I just put this thing together and I didn't provide an external power supply, like a DC battery or DC power supply, and I just put the cell together, attach the wires, nothing would happen, right? I would get no voltage out, okay? Because delta G is positive and E for the cell would be negative. Okay, so the best example of this is the simplest chemical reaction in the world, and that is the electrolysis of water, breaking down water electrically, okay? So this is a chemical reaction that you could have occur in a reaction, in an old-fashioned reaction vessel. You just have to be at very high temperatures in order to make it occur. And that is because water is relatively stable. So what is the chemical reaction that we're talking about? Well, the overall reaction is two waters. Think about this happening in the atmosphere. What's the likelihood of this happening? Smashing into each other, okay? Undergoing a chemical reaction where they break down to make hydrogen and oxygen, okay? So the one thing that we should do here is we should balance this. So let's put this 2 over here, okay? Okay, so 2 waters make 2 hydrogens and an oxygen, okay? Well, much easier to do this in an electrochemical process that I'm going to show you now than it is to just do this in the atmosphere. This water does not want to break down this way. If water was going to break down any way at all, it would break down heterolytically to make H plus ions and OH minus ions. We saw that in the acid-base chapter. Breaking down homogeneously in the gas phase to make hydrogen and oxygen is very difficult to do unless you do it electrically like we're going to do right here. Okay, so here's what I do. Okay, let me show you the setup first and then we'll talk about the half reactions. If I take a power supply, okay, a DC power supply, so just like a battery, where one side of it is positive and the other side of it is negative, and I stick 2 electrodes into the same solution of water, okay, same solution of water, just a regular solution of water. As long as it's catalyzed with some acid, so I have some acid in here because that'll just help the reaction go a little bit faster. So just add a little acid, even though it doesn't participate in the overall final balanced equation, it will help the process along, and you'll see why, because you need these acids are part of the individual half reactions. Okay, so first I have it at 0 volts. Let's say I have an adjustable voltage, right? So first I have it at 0. Nothing happens. I don't see any bubbles coming off of the 2 electrodes. Then I get to 1 volt. Still don't see anything. Then I get to 1.2. Still don't see anything. All of a sudden I get to 1.3 volts and bubbles will start to come off of here and bubbles will start to come off of here. I'm actually generating gases from the water itself. The water is not boiling. Those bubbles are not water molecules in the gas phase. The bubbles on this electrode, I'm going to prove to you in a minute, are actually oxygen molecules, and the bubbles coming off of this electrode are hydrogen molecules. If I wanted to collect them, I could hold a test tube over here, right? Put this in a glass container, and I could collect the 2 products. And they're both very valuable in industry. This is how you make hydrogen, okay? The easiest way to make hydrogen is just make it electrically. You provide the electricity, generate the hydrogen, and store the hydrogen. So not a bad way to make oxygen too, because you can use this in hospitals, right? Hydrogen we would mostly use for burning, and oxygen supports combustion, so they're both valuable, okay? So you don't have to have any fancy process, you can just do this. Okay, so let's talk about what's happening. Well, what is happening is that at the cathode, right? So the cathode is always the place where reduction takes place, right? Oxidation is always the place where the anode takes place. So let me start with the bottom one. I probably should have written this one up here, okay? Because I want you to think from left to right, do the oxidation on the left always. And so the oxidation, guys, always happens at the anode, right? Those guys are hooked together forever. Vowel, vowel, okay? I have a platinum electrode. I could have any kind of electrode, but platinum would be the best. It's got a wire coming off of it, and a wire going over, and another platinum electrode. So these electrodes are the place where the chemical reactions are happening. I'll show you the shorthand notation in a second, but they don't participate in the reaction themselves. They just facilitate it, okay? The difference is I have to pull the electrons. They don't want to come. They don't want to happen on their own. So how do I force them to come? How do I draw them out? By making this side positive. So if this side is positive, then the electrons are going to be opposites attract, right? So electrons are going to be sucked up of here and go towards the positive. They're going to go towards this part of the battery. So I'm going to be vacuum cleaning off sort of the electrons, are pulling them off into the wire. Now the power supply jacks them up, gives them power, jumps them over the hill, and they come down the other side. It's kind of like an uphill reaction, like a pump, right? I'm electrically pumping them up. Here they come down the other side. This reaction doesn't really want to happen so badly either, so I force it to happen by having this guy negatively charged. If there's extra electrons around here, I can get this reaction to happen. Okay, let's see what the two reactions are. So happening over here, I have a water molecule, swims a little bit too close to the electrode, okay? Gives up, turns into oxygen, okay? When it turns into oxygen, it also creates 4 hydrogen ions, so oxygen comes off, plus 4 hydrogen ions, plus 4 electrons get sucked off, pulled up through this electrode, and over to here. Now, the 4 electrons go uphill, right? They don't want to happen. Look how that guy has a negative cell potential. I would look this one up in the table, right? In the back of your book, I would find it written the other way because they always write them as reductions, and it would say positive 1.23. But since I need it this way, I turn it around, I get negative 0.23. That is uphill. That's terrible. It takes 1.23 volts of electricity to get that thing to happen. That does not want to happen. To get that guy away from here does not want to happen. So now here comes our 4 electrons down the other side. Well, down the other side is a much simpler process. I have hydrogen ions who swim too close to this negative electrode. Look, positives go into a negative. They're sucked over there, right? Opposites attract. That hydrogen ion swims over. At the same time, another hydrogen ion swims over. It takes 2. They swim over. Each one of them grabs an electron, right? Becomes a hydrogen atom for a millionth of a second, then hooks up with another hydrogen atom to make hydrogen gas. Remember, hydrogen is diatomic. It would much rather be H2. So that's all happening right on the surface of this platinum over here. Hydrogen ion comes over, other hydrogen ion comes over. Each one grabs an electron, and then they hook up and make a hydrogen molecule. So that's the bubbles coming off of here. What are the bubbles coming off of here? Water molecule swims too close, okay? Loses 4 H pluses and 4 electrons. Okay, let's look at it like this. Each oxygen loses 2 H pluses and 2 electrons, leaving a naked O atom, right? Each oxygen here is in the oxide form. It's got 2 too many electrons. So each oxygen loses 2 electrons, so 2 oxygens in the 2 waters lose 4. They also, all the hydrogens get stripped off. So you can think about the H's going off as H plus, and now I have 4 oxides, 4 O minuses. Well, those 4 O minuses, each O minus is going to lose 2 electrons, okay? And each O, so not 4 oxides, 2 oxides, right? So 2 oxides, each one is going to lose 2 electrons to make 4, and then each one is also going to lose 2 H pluses. So that makes 4 because there's 2 of them that's happening too. So water is going through this process, hydrogen ions are going through this process. Okay, where's the charge neutrality? The charge neutrality is H pluses going this way, negatives going that way. So over time, one side doesn't get more than negative. As soon as I turn the voltage off, party's over, right? As soon as I take this battery out, the bubbles will stop coming off. This is a neat process, something you could do in the lab. Okay, let's put these together. If I look this one up in the back of the book, we talked about this. This is the standard half potential. It was defined as 0, right? All of the ions in solution, their potentials are relative to the hydrogen one. So this is exactly the way you're going to see it in the book. It's happening at the cathode, and it is a reduction. And it's 0 so that it's the standard for other ions. Like if you wanted to know what happens when sodium gets reduced, when Na plus gets reduced, or anything undergoes a reduction potential, their potential is relative to the standard, which is the simple hydrogen half cell, this guy right here, okay? So that's the process. Okay, last thing I have to say, oxidation is going to always happen on the left. It's always happening at the anode. Reduction is happening on the right, always happening at the cathode, but this is different from the voltaic cells. Here I have to pull the electrons over. Remember, when we did the voltaic cells, this guy over here, the anode was negative, and this one was positive. So that's what switches, okay? Oxidation still at the anode, reduction still at the cathode. This guy, though, is positive, right? Because I want to draw the electrons out. Okay, so the last topic that we're going to talk about, so that's an important reaction for you to understand. The last topic that we're going to talk about is the stoichiometry of electrolysis. So this is neat. I can actually quantify, even back in my reaction here, I can measure how much the voltage is, but I can also measure the electric current that goes through. And the electric current, remember, is the movement of electrons over time. It's the charge per unit time. So if I want to make a certain number of grams of oxygen, right, and a certain number of grams of hydrogen, what I could do is I could time it, look at what the current is, and leave it on for a certain amount of time, because current times time will give me electric charge. And then I can say, oh, how many electrons were transferred, and say, okay, in this, this is a 2 electron, this guy over here is going to get multiplied by 2, right? So this is a 4 electron process. So for every 4 electrons that gets transferred, 1 mole, right? Let's look at the overall. For every 4 electrons that gets transferred through the wire, 1 mole of oxygen is created, and 2 moles of hydrogen is created. And if I know the number of moles, then getting the grams is easy, right? I can get the grams from the moles by just multiplying by the molar mass. So this guy multiplied by 32. This guy would multiply by 16 times 2 is 32, and this guy I would multiply by 2 for hydrogen, okay? So here's another version of it. Let's plate out some silver. Now the cool thing about this electrochemistry is there's actually no net chemical reaction occurring. I'm going to, at the anode, I'm going to have silver going into solution, and then at the cathode, I'm going to have silver plating out. So the chemical reaction on the left-hand side is going to be exactly the same as the chemical reaction on the right-hand side. So in theory, I shouldn't have to provide any voltage. So let's take a look at what's going on in the cell. Okay, again, this is not going to happen naturally because it's a nothing reaction, right? So nothing wouldn't happen. I just put the stuff together. But as soon as I turn the power on, it would be very easy. Any electricity going through here at all would start the process. And the higher I turn it up, the faster I could get it to go, because the current would go up if I increase the voltage, right? My job when I increase the power is basically turn up the voltage. So if I increase the outside voltage, I can increase the current that goes through, okay? So that's what, so who would be doing this? A jeweler would be doing this, okay? So here's what you do. You have a piece of silver, okay? Like a bar of silver that you get from the factory, and you dip it into silver nitrate solution. So you have it in silver nitrate solution, okay? So that's on one side. So this bar of silver would stay in there until you used it all up, and then the jeweler would get another one and stick it on there, okay? Now, somebody comes in and they have a copper ring, okay, and they say, hey, you know what, this is a cheap-looking copper ring. I don't like the red color. You know, my boyfriend gave it to me, or my girlfriend gave it to me, and, you know, they're cheapskate. They didn't even give me silver. So can you silver plate this ring for me, sir or miss? Okay, so you say, absolutely. You take the ring, okay, you weigh it first so you can see how much it weighs. So now it's copper, okay? So it has a certain weight. Let's say it weighs 1 gram. You attach electrode to it, so you could have, think about a little alligator clip, okay? This guy, and I set up the circuit, and it goes around. Now, as soon as I turn it on, if I want the silver to plate out on this side, I've got to make this side positive and this side negative, because I need to suck the electrons off of the silver here and deposit them over here. So the left-hand side is always going to be positive. It's going to be where oxidation takes place. Oxidation always takes place at the anode, and oxidation is positive in an electrolytic cell. This kind of cell, a non-spontaneous one. The electrolytic ones, I need to make the oxidation positive, Okay, all right, so what's happening at the left-hand electrode? Our favorite thing, oxidation. The silver is going to go into solution. So silver solid sitting on there. Think of the atoms of silver minding their own business on the electrode. Here's the electrode, the one at the surface right here. He's going to jump in, right? But he can't jump in with all his electrons. He's going to jump in and become silver plus one. And where's its extra electron going? The extra electron goes up the piece of silver. Silver is a conducting material. Through the wire, through the battery, gets pumped up with some extra energy, comes down the other side, and is waiting over here. Now, look at this. The silver nitrate in solution, well, if we were doing this under standard conditions, this would be 1 molar, right? The silver ions, one of them would swim too close to the copper ring. Why would it be drawn over there? Because opposites attract. This is negatively charged, and this is positively charged. So I'm drawing this guy this way. Negativeness goes this way, positiveness goes this way, and they meet up on this side. Look, they break up over here. It's wicked. They break up over here, and they meet back up. Now, maybe not the same two, okay? But the silver that goes over here and one that comes up here, they're going to meet up over on the other side. So no chemistry, just plating out, getting something to plate out. Okay, now, so oxidation anode. What's happening over here? The reduction. Okay, so here's the reduction at the right-hand electrode. So we always write that. That's where the ring is. Okay, so I'm having a silver ion come too close, pick up an electron off the copper, and plate out. Now the cool thing about plating, better than painting or something like that, is the plating will occur very equally. First you'll get a layer of silver, then the next layer will come up. You'll never get bumpiness when you plate out, like one side being thicker than the other. Your ring will get plated equally. Just have to be careful where you do the attachment. So they must have a way of doing that. Okay? All right, come back over time. Weigh this, pull this ring out. The ring is going to weigh more than it used to, because now, what does it weigh more by? The extra silver that plated out. This bar is going to weigh less than it used to. The amount that this goes down is going to be equal to the amount that this goes up. All you did was transfer silver from up here to over here. Okay, so the jeweler who's plating this out for you and doing you a favor and plating it out has a choice. They could either weigh it, or what they probably do is they say, oh, if I know, right, if I know the current that's going through it times the time, right, the current times the time that I leave it on. So let's say this is 1 amp going through it for 1 minute, right? So that would be 60 coulombs would have been transferred, because this is amps or coulombs per second. And if I leave it on for 1 minute, that's 60 seconds. So what do I do here? I take the amperage, the current that's going through here, okay, not the voltage, the current, and I multiply it by the time. Okay, now I use my Faraday as a conversion factor, okay, and I convert from moles of electrons to moles of, so I'm gonna do an example in a second. So moles of electrons to moles of silver that's transferred. And then the last thing, I can get the grams. Okay, so let me do an example here. I'll write it in pen, it's probably easier to see. Okay, so let's say I ask you this question. How many grams of silver, will be formed if the electrical current in the cell is 1.0 amp, okay, and the cell is left on for, I want to make a lot of silver for 10 minutes, okay? Okay, so the first thing, get the time in seconds. So I have 10.0 minutes times, there are 60 seconds in every 1 minute. That gives me 600 seconds. Okay, so for 600 seconds, this thing is running. Okay, next thing, get the Q. Q, right, is equal to I times T. What's the I? 1 amp. So this is I times T, 1 amp times 600 seconds. Amps times seconds gives me coulombs because this is coulombs per second. So Q is equal to 600 coulombs. Okay. All right, take my 600 coulombs. Use the Faraday, right? The Faraday is the number of coulombs in moles of electrons. So in our case, I need to get rid of the coulombs, so that's going to go in the denominator. So if I'm going from electric charge to moles, I put the Faraday in the denominator. So 96,500 coulombs of electric charge are in each 1 mole of electrons. Okay, all right, last piece, or I should say second to last piece, look at the balanced equation and see how many electrons were transferred. Well, we had such a simple one. This is a 1 electron oxidation and a 1 electron reduction. Remember, the oxidation and reduction have to be the same. So this is a 1 electron process. So for every 1 mole of electrons, I get 1 mole of silver that were played out, right? Okay, I got a 1 electron process. If you went through and ran through the balanced equation and there was 2 electrons here and it canceled with 2, you'd have to put a 2 there. And then the last thing, just multiply by the molar mass of silver. 1 mole of silver has what weight? I'll look it up for you. Silver is 107.86, so we can make it 107.9. Okay, so we're going to make let's see how much we can make. We're going to make that much. So 600 times, I'll go straight across the top. 600 times 107.9 divided by 96,500. Okay. I got an answer of 0.67. That's just quite a ring, okay? So we added 0.67 grams of silver to the copper ring by getting it to plate out, okay? So go back and look at a picture. This electrode should be 0.67 grams lighter after the process, and the ring should be 0.67 grams heavier, okay? The concentration of the silver in the solution shouldn't change, right? That's pretty neat. And neither would the nitrate. So in these plating baths, you can do this over and over and over again. And then the jeweler would just buy these different bars of silver, or you can get things to be gold plated. That's how they do it, okay? Or platinum plated. You just release it from one side, you oxidize it from one side, and you reduce it onto whatever material you want it to be plated out. Same thing if you want a chrome bumper. You dip the whole bumper in the solution and you get a thin coating of chrome on your steel. And the chrome coating makes the bumper look nice and shiny, and it also protects the steel that's underneath. Okay, last thing you would do if you had a plating bath like this is you probably don't want it to be in an oxygen-rich environment because you don't want things to become sort of all oxidized. So they probably bubble some nitrogen gas through this, or just have it in a space that has nitrogen above it, because oxygen would hinder this process. So the best thing would be if they were dipped all the way under the solution, and you probably are doing this in an environment that doesn't have a lot of free oxygen gas molecules floating around. And that's very easy to do. Just have it in a room filled with nitrogen. Nitrogen is cheap. Or bubble, just have a bubbler in here and constantly be sweeping out this solution so that there's no oxygen in it. Okay? All right. Here's a different example that I have at the bottom here. Okay, so I did the one for, this is for 1 hour at half an amp. I just did, how many grams would be formed? 10 minutes at 1 amp. Okay, so in this one, you guys can go over that yourself. Since it's such a longer amount of time, it was for a whole hour. So instead of 600 seconds, it's 3,600 seconds, but I had half of the current. So in this case, I'm able to plate out 2.01 grams. Okay. And here it's written out straight across, so you have it in your notes. Okay, and the last page is chapter 20 equations. Okay, this relates chapter 19 and chapter 20. When E for the cell is positive, that's a spontaneous reaction. That would be a voltaic cell. You'd have to separate and have two different beakers. Look at this one, guys. Last two that we just did, the electrolytic cells. The plating out of the silver and the decomposition of water. I didn't need two beakers because water is not going to decompose on its own, and silver is not going to jump onto the ring on its own. You need to turn the power on to drive it. Okay. And again, N, it's going to depend on the particular chemical reaction. It's the number of electrons that are transferred when you have a balanced oxidation reduction reaction. It's a number. Okay. Faraday constant, you can memorize it. It's the charge on 1 mole of electrons. Here's the relationship for E for the cell when you're at equilibrium, right? E for the cell and K. What is the equilibrium constant for the cell when you're under standard conditions? Okay, and the E for the cell will come out in volts at 25 degrees. Okay, this one does equilibrium. This one does, if you want to know E for the cell under non-standard conditions, and you have it from standard conditions, right? Remember, these you tabulate from the back of the book. These you tabulate from the back of the book. Okay, use that same number. Remember, use the LOG because this 0.0592 already factored that in. So you need the log base 10 here. Okay, again, the values will come out in volts and they're at 25 degrees. Here, E for the cell is equal to E ox plus E red. This is under any conditions. This is under standard conditions. So again, back of the book, any place you see a 0. And I'm going to quickly grab the book. And the last thing we learned is if I want to know the charge, it's just the current times the time. And then I can do stoichiometry with it using the Faraday. So I don't have another formula for that. It's not really a formula, but it's this idea of taking I times T, get the number of coulombs, then go from coulombs using the Faraday to moles of electrons, then look at the balanced equation and go from moles of electron to moles of what you're interested in, then multiply by the molar mass of that substance. Okay, last thing I want to just show you, remember those E0 tables? Really important, right after the thermodynamics, kind of related to the thermodynamics, right? None of this tells you anything about kinetics. It doesn't tell you how fast the reactions occur. It tells you if they occur spontaneously or not. Don't confuse those two things. And they are right here, right? There's one whole page of it in your book, right? Every single one of them has the electrons on the left-hand side. You cannot use two of these together the way they're written because I'd have electrons getting sucked in and none of them being captured. When you put them together, can't have oxidation without reduction, right? Can't have reduction without oxidation. So you're going to have to turn one of them around. Okay, which one? you're going to have to turn, if you want it to be a spontaneous reaction, you need to turn the one around that's going to give you a positive number when you put the two pieces of together. So let's say I wanted to put this one together with this one, right? Actually, let's do the first two on the top, right? Why not, right? If I want to put together this one and this one, and I have to have it become positive, right? So it's not going to be super positive. Let me make this a little smaller. Okay, so this one's 0.8, and this was negative 0.83. I need to turn this one around to turn the water reaction around if I want water to react with silver to undergo this. And that's perfectly possible. You can put those two together. See, why turn this one around? Because now I have negative 0.83 becomes, actually this one would be spontaneous already. This one would become positive, right? So negative 0.83 becomes positive 0.83. Leave this one alone. So the total cell potential, when I put this together with this, would be positive 0.83 plus 0.8. So that would be 1.63. If I did this under standard conditions, right, it would be silver ions going to silver and water going to hydrogen and hydroxide. Now, that's pretty cool, right? So this one would be spontaneous. So I could reduce silver okay. I could reduce silver to silver ions, reduce silver ions to silver with water if I provided those two electrons. Okay, so this guy gets turned around the other way. Oh, excuse me. If I'm turning it around, that makes more sense. Hydrogen plus hydroxide plus silver ions can make silver and water. Pretty neat. Okay, so I could hydrogen, gas, hydroxide, and silver ions to make silver. Okay, it would be a spontaneous process, right? Because the hydrogen would want to get oxidized, and the voltage would read 1.63, right? Because I turn this around, add it up to this guy. Okay, what conditions would I have to maintain? Well, hydrogen is a gas, so the hydrogen I'd have to constantly keep a partial pressure of 1 atmosphere of hydrogen. Since it's the only gas, that's the only thing that I would need. So I'd be doing this in a chamber that had 1 atmosphere, and I'd measure the pressure all the time. That 1 atmosphere of hydrogen was always present. Okay, all right. This would have to be silver ions would have to be 1 molar. Water doesn't matter, right? Because it's not a solution. And what would the hydroxide ions have to be? The hydroxide ions would also have to be 1 molar to have that 1.63. Okay, so this would be a very basic solution in the presence of hydrogen. Okay, so actually, might as well. I'll just take a couple of more minutes. Might as well do it. Right? I'm just gonna write down what the tap reactions are. Right. Right. So I'm leaving the first one alone. So I leave it alone. That's going to be silver ions, aqueous, plus 1 electron, goes to Ag, solid. So I'm in the silver making business. And what's my cell potential? 0.80. Okay. I rewrote it exactly the way I see it, so don't touch anything. Okay. This is E red. E0 red. Okay. Let's take that first one and turn it around. So I'm turning it around. I've got hydrogen gas plus hydroxide react to make 2 water molecules in the liquid phase and 2 electrons. Okay? All right, since I turned it around, right, this here, guys, is opposite to what's up there. I need to turn the voltage around. This guy becomes positive 0.83. And since over here it was a reduction, and here it's an oxidation, this becomes E0 ox. Okay. This is a 1 electron reduction. This is a 2 electron oxidation. I have to multiply this guy through by 2. Okay. going to throw two passes, got to have two receivers catch them. They can't push electrons out into nowhere. What cancels out? The electrons have to cancel out. Anything else cancel out? I don't think so. So my overall reaction is silver plus hydrogen gas plus two hydroxides to make two silvers. I can get the silvers to plate out, right? I'm going to show you where they'll plate out in a second, plus two water molecules. So nobody cares about water. And my overall, add this guy and this one, E ox plus E red is going to be 1 point, add those two numbers up, 1.83. Oh, sorry, 1.63. Okay, that's what my voltmeter would read. Okay, super fast. Let me draw it for you. Okay, this is positive. This is spontaneous. This is a voltaic cell. I don't need a battery. I do need to separate the two materials though, because if I don't, they're not going to react through the wire. They would react head to head. They would just react right in place, and I don't want that to happen. So here's my first beaker. Here's my second beaker. Okay, always put the oxidation on the left. So this is oxidation. Oxidation always happens at the anode. Okay, and this guy is naturally negative, anion negative. This is a naturally occurring cell. Okay, here's my piece of, since this guy here is being oxidized, I need an inert electrode. So I'll take a piece of platinum, stick it in there. Okay, what's this solution have in it? This solution has 1 molar hydroxide ions. They could be sodium hydroxide, who the heck cares, right? It's the hydroxide that counts, right? And I have it in a chamber, closed up chamber, that I'm always providing hydrogen gas to it, right? So better, sometimes you can see a bubbler come in. So it would be a tube, and it would bubble the hydrogen gas or mix the hydrogen gas into here so that this was at 1 atmosphere of H2 pressure. The partial pressure would be 1 atmosphere in there. Okay, so keep that hydrogen gas pressure on. All right, what's going on? Oxidation, anode, negative. Reduction, always at the cathode. These two things, doesn't matter if it's voltaic or electrolytic. This guy is positive because it's a voltaic cell. Voltaic cell happens on its own. Okay, what's in here? What's being reduced? I need a piece of silver. Inside, silver ions at 1 molar. Here's my piece of silver. Okay, last thing I need to do. Just need to connect these two things. Put a voltmeter across them. Make a salt bridge so that the ions can travel back across. When I read this meter, sorry this is so sloppy, when I read this meter, what's it going to read? 1.63 volts, because I have this at 1 molar, I've got this at 1 molar, and I've got the pressure of the hydrogen at 1 atmosphere. Okay, so that was just taking two random ones, the first two on the list. You can get anything in theory to react with anything else, and you can figure out what the potential is. Okay, all right, that's it for this chapter. Thanks, guys, and bye.